Hello, this is Ashkan. Welcome to another video from NoOp Army about the AI algorithms that you can use in your games. So there are different AI algorithms which can be used in your game. But the first question to ask is what's the goal? Why are you designing the AI? How you should design it? So an AI for an agent basically is the code that makes the agent behave automatically in the game. But what's the goal of the behavior? The behavior should be fun, obviously, for a game. It should be immersive, so the player feels that the agent is somehow real. If it's like a human character, a guard, it should behave like a guard. It shouldn't behave like something else. But it should be like mm, a guard which is fun to play against. It's the goal is not to be 100% accurate, perfect guard which can find and kill every predator. But what are the technical goals? Basically, the AI should be controllable by designers, and it should be changeable. So when you have a guard AI and you decide that okay, I want the guard to have a coffee drinking behavior. So after it gets tired, he or she goes to uh, the coffee machine, get a coffee, and starts drinking it unless something alarming happens. And you should be able to easily add that. Or if you decide later on that, okay, I do not want the coffee drinking behavior, it doesn't look cool, or it's not helping the game, it should be easy to remove it without messing up with the rest of the AI. Customization is an important feature, and being able to do late time changes is an important feature. Also, it should be easy to manage for both developers and designers. So, if you want to code a new behavior, it shouldn't be too hard. And it shouldn't be too hard for designers to understand how the AI works because some systems lean better into designer type of thinking or developer type of thinking. And also, another important thing which shouldn't be missed is to be able to solve edge cases. So let's say you have a guard, and your guard uh, basically gets alarmed when somebody comes nearby, like in 15 meters or something, or if a loud noise gets generated. But there is an edge case that somebody comes close and at the same time somebody else generates a very loud noise. Which one the guard should pay attention to? It should be easy to basically modify the behavior and do basically make it work the way the designer intends for it to work. It shouldn't be hard to do that. There are four types of algorithms which we'll consider: state machines, behavior trees, goal-oriented action planners, and utility AI. And we'll take a brief look at machine learning and neural networks, but uh, they are not commonly used for these things, so it will not be like a big talk about them. So what's a state machine? A state machine is basically you defining a set of states like state A and B and C and D, and then you define when you transition from each state to another. So let's say you have a guard and it has a idle state. It also has a alarmed state, a shooting state, and I don't know another. Drink coffee. Now you should have definitions of the states and also transitions between them. So when does a guard can get alarmed? When it's idle, there is some transition from idle to alarmed. And also when the guard is alarmed, there is a transition back from alarm to idle. And you should define all of these transitions so each state should know what other states it can go to and when. And then when you add a new state, you should define transitions from all the previous states to this new one. Let's say we decide to add a behavior to basically destroy the building because it no longer can be guarded. This state is something that potentially can happen. Sorry for the bad text position. Anytime. So all other states need a transition to this. So let's say we are shooting and we see that okay, we have no more bullets left and the building is too important to basically be in the enemy's hands, so we should exploit, destroy it. But this also can happen when we are idle. If we can see that there are 15 enemies and you have to add transitions for every possible position that you could be, and you would need to destroy the building. So that's how state machines work. They are easy to understand and they're easy to make basically a sequential deterministic AI with, because you can know, okay, when I'm shooting, I can only go to two other states, alarm and destroy the building, for example. I never can go from shooting to drink a coffee because it doesn't make sense. Mm, while shooting, you are basically having an enemy. If the enemy gets killed, okay, you go to idle. If there is no other enemy around, if there is, you go to alerted mode, alarm mode. So they are easy to understand and they are easy to control because you exactly write from which state to which other state you go to. It's not flexible because whenever you add a new state, uh, you have to create transitions from all other possible states. So you can easily make mistakes, and these state machines can easily become hard to understand if there are like 50 states and 200 transitions. It's not easy to add many actions because like it gets complicated and becomes hard to work with. So behavior trees were kind of an answer. They are usually used more previously before games in used in robotics for navigations and like controlling robots, but they can be used in games. They are better than state machines because you can more easily manage bigger like number of actions, but they are still hard to follow if they become big, and they're still not easy to add actions to. And let me show you why. What a behavior tree is. A behavior tree is a tree of nodes. So you have, let's say, a root node here, a child node. It's a tree, like one directional graph of nodes, which get executed from top to bottom and left to right. So the leaf nodes are your actual actions. So when the tree wants to execute, let's say the same guard, if you had that, this would be called shoot. And the rest will be like added here. The final one, which usually can always execute, is idle. We call this failover action. And this doesn't have a transition. I forgot about it, sorry. Uh, so basically the tree starts here, and usually these nodes, which are not leaves, are conditionals. Like they could be a selector which executes its children until one of them basically fails. There are nodes to execute children until one of them succeeds, and basically what happens is that if this node can execute successfully, this will not move right. So come here, evaluates this. If it's successful, come to this. If shooting can be successful, then it will not go somewhere else. So this node will be something like uh, shoot if you have enemies. If you don't have enemies, then this will fail, and this will come here, and this node will get executed. Let's say this is for alarming. We will say if there are execute this if there are any close enemies, like look alarmed. we can have another here which checks, okay, if there are no close enemies, are there at least sounds to get attentive to? And then if this fails, this will come up here and goes to this node and will try to execute this. If everything else fails, you usually come to this node, which is like something that always executes. And this is like an idle action. And at least in Unreal, there is a concept of service nodes. So, for example, is for updating blackboards and other systems in the game. This executes as long as any of the children of this node, which this is the service node for, execute. And there are like service nodes execute like as long as shooting execute. Let's say whenever you shoot, this decreases the ammo once, or just checks the number of enemies again and put that in the blackboard so the shoot action can check it. Also, there are like non-leaf nodes like parallel, which execute all of their children at once. Let's say this alarm node what has to be executed with this other attention node uh, at the same time. We can put a parallel node here. This is kind of like a programming language. Basically, the selector nodes and the parallel nodes execute based on a condition, and if successful, they will continue. If failed, the next node in the row will execute. So, kind of like a huge if and else statement. They can easily become hard to add because first of all, order matters. So, if you want to add a new action like destroy the building, where should you add it? Should it be checked after shooting? Should it be checked after alarming? And this matters. This is like because the tree executes from top to bottom and left to right. So if the condition for shooting is true and also the condition for destroying the building is true, if shooting is at the left of destroy the building, first shooting executes. If the destroy the building is at the left of shooting, then destroy the building will execute. So it matters which one is at the left side of the other. Uh, at the moment, with this setup, first the conditions for shooting is checked, and if they are true, we will not destroy the building. And it's still easy, but imagine having 100 of these. Like, look at the samples of behavior trees in games which has done this and used this, and this is still much easier to manage than state machines for most people because at least there is an explicit order that you know that okay, this there will be this first and then there will be that, and this is good and easy to use for sequential behaviors like state machines are, but it's still like hard to add actions to and hard to modify, especially late in the project when everything is like big, everything is like cranked up to 11. You have too many actions and too many things to do in all agents, and that makes it like less suitable for games which have lots of actions. Okay, goal-oriented action planners. What are they? First of all, few games used it. Fear and Tomb Raider are the two that comes to my mind. The previous two are used by many games, many games. They are very hard to control because let me show you how they work. The way that they work is that you define some actions and a goal. So action 2, action 3, and each action has a set of requirements and does affect something. And then you have a goal separate from these here. The action planner sees the goal. Let's say the goal is to kill all of the intruders for a guard. And then, based on the current situation, the planner checks all of the actions and their costs and their requirements and finds the shortest path to kill all the intruders based on the cost of the current actions and their requirements. So shoot enemies an action. Uh, idle is another. Find enemies another. let's say doing coffee is another. And each of these actions have a cost associated with them, and also have some requirements. For example, shooting has a requirement of you should have ammo and there should be an enemy. So if currently the world being evaluated doesn't have any enemy involved to kill all the intruders as the goal, you cannot shoot. So this action will not be considered, will not be a part of the goal. The lowest cost when there is no enemy is to just execute idle because it has a cost of, let's say, 1, and shooting has a cost of 3, and also its requirements aren't met. And you don't need to find ammo because like the cost is high, and you like there is no enemy, which is a requirement for finding ammo. This is very hard to control and hard to know why an action gets executed and when, because let's say you have 15 actions and you have a behavior in mind. This is like more like, okay, what are the behaviors that we should do? Let's say there is a noise somewhere and also there is an enemy close by and you have 3 out of 10 ammos left. Based on these costs and requirements, the AI will choose to do either go find ammo or shoot at the current enemy or attend to the noise. And figuring out why and how in each frame what action is selected is not really easy because it's a hidden scoring mechanism that you cannot easily check. Of course, you can debug like every requirement and every cost and see what the path generated is, but when you modify cost to get your desired behavior, all of the other cases get modified too because the cost is modified for all of them. Let's say you want to go find ammo if you have one enemy, but not if you have two, and less than 50% ammo. Then you can like modify the cost of finding ammo based on that and based on the number of enemies. But then it will be modified for all other cases. So they are very hard to control. They are not sequential and you cannot easily do exact specific behavior with them, but they are not easy to debug either. They are not basically, at least to me, they do not provide any clear advantages to utility AI if you want something without explicit order of things. So they basically do not give you the simplicity of state machines and state trees with explicit order and execution time, and they do not give you utility AI's controllability. What's utility AI? We are obviously biased because like we sell these and we use it for these in our games. So in utility AI, you define a set of actions, and each action gets scored of how much utility there is to execute it at the moment. So it is not explicit ordering in this way. It is similar to goal-oriented ones. So there is a shoot action, there is an idle action, there is a find ammo, and there is a drink coffee. And then each of these gets scored every time that we want to decide what to execute. So how do we calculate the score of these? Each of these can have a set of considerations which say how good their score is. So what are the considerations for shooting? The consideration are things like, is there any enemies close by? Do I have ammo? Each of these will return something between like 0 and 1, and then they get multiplied with some modifiers so you do not get penalized for having too many considerations. So let's say they get multiplied. So if you don't have enemies, the score of shooting would be 0. And then everything else always gets scored. So unlike behavior trees, the order doesn't matter. All of the actions always get scored. And then either the highest scoring action or one of the top few gets executed, and then after some time you evaluate all actions again, like I don't know, 2 times a second, depends on the game speed, and you continue. And usually one of the actions always scores something. So idle, for example, gets scored based on if there are no enemies around, you can be idle, and if you don't need to do something other than that, which is important. When you want to add an action, you only like need to you just need to say, okay, I need another action which is destroy the building. You don't need to create any transitions, you don't need to consider any orders. You just need to basically say when it's a good time to destroy the building. And when it's a good time to destroy the building, get scored with all other actions, and then based on how good it is, it will get executed. Now, you still can get incorrect behavior. If you have no ammo, and also you, let's say, uh, have many enemies around, and let's say low health, then this will score high. So, uh, you still can get incorrect behavior, but the incorrect behavior can be much easier debugged because you can see all of the scores. Let's say you wanted to have like destroy the building happen if you have more than 3 enemies and low health and low ammo. Then you just detonate the building. You see that okay, you have 4 enemies, but still it is not destroying the building, despite the fact that you have low ammo and low health. You can just check to see what this action scored. Let's say it scored 0.4, and then you can see that okay, we are trying to find ammo, and find ammo scored 0.9, and you can check the considerations for find ammo to see why at this situation, despite the fact that we have low health, we are getting a high score of 0.9, and then you can change the consideration for health for find ammo. So basically it scores lower when you have low health. So the scoring for finding ammo will get modified, and you consider how many ammo do I have, and also consider health. And the considerations, we did not discuss them much yet, but usually how you code them is that you code a function which returns something between 0 and 1. So if your max health is 100 and minimum health is 0, then you code the consideration to return 1 if your health is 100 and return 0 if it's 0. If it's 50, return 0.5. But you also give the designer the option to modify the returned value using a curve. So a curve like this would mean that if the health is 0, it will return 0. Until near 50, it will return something value close to 0. But as soon as you go like above half, then the score shoots toward the sky and it will return 1, let's say here. So the designers can just modify these curves for considerations to get the exact behavior they want. It's harder to get exact deterministic ordered behavior using utility AI compared to state machines and behavior trees. And if you have a very low number of actions and you always want an exact order of things to happen when something else happened, probably it's a good idea to use state machines or behavior trees. But with games with many actions and lots of things to consider, which you want to modify it again and again and again, this is, in my opinion, the best thing that you can use. Okay, what about machine learning and neural networks? So basically, to recap first, the utility AI stuff. They are harder to exactly control compared to a state machine, but much easier to control compared to like the goal-oriented action planners. But they are still pretty controllable because you can modify considerations, modify the curves, add more considerations, and if you need exact order, you can have a consideration which says if the previous action was shooting, then you can execute this, otherwise not. So it's not impossible to add exact order. It's easy to add and remove actions because you add actions, just set their scores, and you don't need to consider transitions or orders or weird like pathfinding behavior and things like that. It's very easy to use in situations which you do not know exact best thing to do, but you roughly know how to like find out what's the best thing to do, which is the way that humans think. More and more games are using it. The Sims, Guild Wars are the two famous examples which Dave Mark brought up in his talks, and talked to like the guys behind them. He talked to the guys behind Guild Wars, but not the Sims actually. Now, mm, machine learning is like very useful for certain things, but character AI is not one of them because you need to train lots of like with lots of data, and then it gives you a black box. And if the behavior is not what you want, then you have to retrain. You don't need to. You cannot do anything else. You cannot modify part of the behavior and let's tell the AI, okay, I don't want to find ammo if you have 20% health. That just detonate the building for God's sake. If there is some specific situation that arises that you see that your AI did not terrain correctly, you have to just reterrain it and hope for the best. And that's why not that many games use it. Like I know that Forza uses it for driver behavior, and it's good to for bots maybe in some other types of games too, and probably it's used successfully to create more bots. But to create like interesting NPC behavior and agent behavior, this is hard to control and hard to know how to change and how to control it if the end result is not what the designers wanted to. You have to redesign your reward functions and train terrain basically again and again and again and hope for the best. So why shouldn't we combine these is something that many people might ask and get excited. Unreal does this. Their state trees, their new state trees are like that. They are state machines with behavior trees combined. And actually, state machines are the only ones which, at least to me, make sense to combine with the others. Uh, but like it can be done, but how much useful it is depends on the case. So you cannot just willy-nilly say this. If you have a use case and say, okay, in my game, I know that the characters always are either in one of three states, A, B, and C, and then each of those states have some actions, then you can say, I have a good case for combining a state machine with whatever else I'm using, like a behavior tree or utility AI. But for many situations, like you don't have to go that far, and just you can use bucketing of your actions, and easily you can do that by having multiple behavior trees or multiple buckets of actions for a utility AI, and then say, okay, if these conditions are met, then use actions in bucket one, otherwise use actions in bucket two, or use actions in bucket three in this other specific situation. Now, still, you can combine them in other ways. Like a behavior tree can have subtrees which are a goal-oriented action planner or utility AI, but these usually too complex, doesn't make sense to designers and doesn't provide you that many advantages because these approaches are sometimes contrary to each other. Like if you have designed your AI based on a goal-oriented system, then like how I cannot even fathom how you can combine them with behavior trees and get a good result because you are either for actions considering scores and requirements and shortest path, or you are adding them in a specific order in a behavior tree. uh, what else? Basically, mm, I don't know. I That's what all I can say. You should have a specific use case, and usually it's hard to find a use case for having a like other than having something which chooses the high level and then low level is the other thing. Like let's say you have a strategy game and you want to like the low level entities because they are simple. You can use just simple state machines. Okay, if you want to move there, move there. If you want to shoot the enemy, just shoot the enemy. But the high level is chosen with utility AI or behavior tree. That I can make sense of, and that's something that's probably done. But combining like two of these for a specific level of the AI, other than like the uh, buckets and sets with a state machine, which we already discussed, do not make sense to me. Aren't these all good? Like we are in the age of this, literally. Let's let's not make tech postmodern, okay? We ruined everything else, music and arts and like movies and everything else. Let's not do that to tech. Like different solutions have different advantages, okay? So If you use a behavior tree, you get exact order, you get deterministic execution. If you use a utility AI, you get easy addition of new actions and easy modifications, but you do not have exact behavior. So there is real difference between these. If you stretch them, you can make them look like the other one. You can have a behavior tree which basically has nodes to evaluate utility scores of its children and then chooses one of the children based on their utility score, and but it's no longer the concept or the philosophy of the behavior tree. It's a Frankenstein monster that you made just to score a point or whatever, because at least in all cases that I've seen, uh, you basically cannot change something enough that it's not the old thing anymore and call it like the same thing. If you add wheels to a ship and it no longer needs water and can drive on the ground, it's no longer a ship. So I mean, I cannot say anything more like constructive than this. If you think you should be able to do that and you still can call it a ship, then okay, go ahead. Like all of these are the same and everything is like the same. Nothing matters, whatever. So why most games use state machines and behavior trees? Because these are like the oldest things that are used, and older things are used more because people know them more and they are more useful. And older games had less actions, they had simpler behavior, they had less number of behaviors, they were less things happening. Like imagine the oldest games like Super Mario Brothers or even Doom. How many things were happening? There were a few actions and specific behaviors needed. But today, with the survival games and simulation games and lots of characters with lots of actions, utility AI to me is a better approach because you have to have lots of things to happen and in a good way, which makes the player feel good and let them have fun. Of course, many teams are more familiar with the other approaches and they will use them, and I cannot and do not want to convince them. But if you are starting from scratch, or if you have used blend tree behavior trees in an older game and you feel that you had more issues than you needed to, maybe give behavior trees a shot. So basically, it comes down at the end of the day to these two. Do you want order and structure, or having a scoring mechanism? Order means that you should basically hold more than one thing in your head and say, okay, I want first see if I need to shoot, and if not, then I will check if I need to do X or Y, or in the case of state machines, I want to know which states I can go to from shooting. Should I drink coffee? Should I detonate the building? You should think about multiple of these at the same time. Also, order means that it's easier to create exact behavior. So let's say you want an agent to, as soon as you saw somebody, you get alerted. If they come close to you, you start shooting at them. If you want this exact behavior always and all the time, order is good for you. So behavior trees and state machine. But scoring means, roughly speaking, the behavior can be set easily. So, but it's not exact behavior. So you give a scoring mechanism to shooting, so it gives a high score when the enemy is close by and you have an ammo. But also you give a score to like find ammo when you have low ammo and relatively less danger. Sometimes when you have like 20 actions, it might not, like you cannot say exactly what will happen in a specific situation. You can just observe the situations and see if what behaves is good or not, and then modify the scores based on that. So if you were using a scoring based approach like goal oriented or utility AI, you should think like what you do in real life instead of what you think as a program. When you have exact order, state machines and behavior trees are simple programs. That's what they are. They have conditions and jumps. But if you use a scoring mechanism, you should think like in real life. You will be like, okay, if I was a guard and I wanted to find ammo when I have low ammo, when would I do that? Okay, I'll do that when there is no enemies around, if when I have relatively high health and low ammo, and then create a scoring mechanism based on that. And it's less abstract. It's more like real life. You are not thinking about transitions or conditions or orders. You are thinking when it's a good time to do this. And if you observe the behavior and it's not correct, then you modify the score basically to be more relevant, more basically like how you want it to behave. So behavior trees and state machines and graphs are basically are more concerned with what's the current state, what are the next states which I can go to. But score are more uh, independent. Basically, scores are more considered with how good the current action is to execute at the moment. Basically, the current state doesn't matter most of the times. How good it is to find an ammo. If you want it to matter, you can add a consideration and say if the current state was trying to reload, then drinking coffee doesn't make sense. So drinking coffee only can execute it if you have been idle for at least 5 minutes. You can do that, but you don't have to for most actions. And if that's what you need, then you can add it, but you don't have to be concerned with that, what the current state is. You can just score the actions based on how important they are to do at the moment and how good they are for the current moment to execute. It's easier to think about things one at a time, so scoring based actions should be easier to think about. At least it comes more naturally to me, and I have seen others which say the same thing. And edge cases can be resolved in both cases by observation. So if you have a state machine or behavior tree or utility AI, edge cases usually are like bugs. You are playing the game and you see that the agent is acting stupidly. And then you see what the situation was and what you think you should have happened, should have happened, and what was happening instead. And then either modify your state or tree or scores so that happens. It doesn't like make much difference other than how easy it is to modify something. In a state machine, usually you will find out that you need to add a specific transition from a state to another state, which is more desired for that specific situation. But you might realize that, okay, I need more transitions like that in other places, and it starts to look like a spaghetti. In a behavior tree, the harder thing is to find where in the tree you should add these new considerations or which condition you need to change. But in a scoring system, basically, you are like, okay, I should have realized that finding ammo is important, kinda, even if there are enemies around and you have zero ammo but high health, you could go into danger and try to find ammo to be able to kill. And you don't need to modify the other actions usually, and their scores most of the times. So that's it, me trying to sell utility AIs to you. I cannot do it as well as they want, but tried my best. These are the contact informations that you can use, our website, support email, and also Twitter/X account. We have also Discord server, which will be linked in the YouTube video. And we sell utility AI libraries with influence maps for both Unity and Unreal, which you can buy at our website. I hope it has been a good ride and enjoy programming.